Hello, everyone. I'm pleased to be here today to discuss what non-engineers need to know about structural masonry. My name is Beth Suminski, and I'll be your presenter today. There is a huge misconception in a large percentage of design professionals today that masonry is not a competitive building material, that it is too archaic, too costly, too limited. That misconception couldn't be farther from the truth. Masonry today is more cutting edge, more efficient, and more flexible than we give it credit for. Today, we will discuss these learning objectives. We will review structural masonry basics. We will discover updated design criteria and design methods for masonry. We will learn to design economical masonry walls, and we will explore structural masonry details. A little bit about me. My name is Beth Suminski, as I said, and I am a licensed structural engineer in California and a professional engineer in California and Arkansas. My background with a bachelor's degree is in civil engineering, and then I obtained my master's in structural engineering from Stanford University. I worked in Southern California for 10 years as a consulting engineer. I worked at Bentley Systems in the structural engineering software department for 9 years, and then I joined Force Consulting in 2016, where I get to utilize all of my design, presentation, and software skills in one place. Force Consulting is a team of engineers with extensive masonry design experience. We are a consultant for IMI since February of 2010, and we have a lot of specialty in structural masonry design. So the fact that I began my career in Southern California greatly impacted how I perceived masonry design. In San Diego, masonry was our material of choice for a multitude of structures, for military barracks, for park restrooms, for school gymnasiums, and on and on. We had high seismic, we had stringent DSA requirements, we had military blast requirements, we used high strength, heavily reinforced, specially inspected masonry, and it handled it all. So it came as something of a surprise when I moved east and learned that this fondness for masonry wasn't shared by all design professionals. Today's presentation is intended to point out some of the misconceptions that have led to this and to talk about why masonry is in fact an excellent building solution. So we will discuss these topics today, like I mentioned, the structural masonry basics, the masonry systems overview, stair towers and shaft walls, interior partitions, masonry and steel interfaces, and then lintels. And associated with lintels, I'll get into some joint spacing as well. So let's start with some masonry basics. How to spot a bad or a good design. First of all, what does good versus bad mean? And usually we're referring to cost. And much of structural masonry design today is inefficient. It has design flaws and it is more costly than necessary. It's not just costly, it's just more costly than necessary. In bidding masonry, many times previous projects are used, and that leads to an inflated estimate if those previous designs were not designed efficiently. And we'll take a look at some of the key items that are wrong in these older, inefficient designs. Number one, engineers are using the wrong strength. We're not using capacity of masonry already in the project. We're adding reinforcement to walls that don't need it, and we're making poor choices in our materials for lintels. So let's step through some of the typical design elements and look at this bad design and how we can turn it into a good design. First of all, I mentioned the strength of the masonry. Historically, F'M has been set at 1500 psi. We will get into that in more detail later on in the presentation. We need to move away from that value and go up to 2000 or even 3000 psi. We've located control joints at opening edges, and we need to move away from that, literally, from the edges of openings. We've specified steel lintels, and we can be using masonry lintels in most of those situations. We've been reinforcing all partition walls, but most partition walls are unreinforced in a good design. And then we need to get away from this idea that masonry needs to be non-load bearing or that masonry can't be designed for larger structures. And we need to start utilizing load bearing masonry and masonry shear walls. So beginning with the structural concrete masonry basics, masonry can be used for bearing walls, partition walls, shear walls, firewalls, shaft walls, basement and frost walls. It can be a finished trade, so we have nice tight tolerances with this material. There's no lead time for production review and approval of shop drawings. Whereas with steel, you may have a significant amount of time eaten up before you even begin the project with the shop drawing creation. It adapts easily to field changes. We had one person say, with the masonry, you can just pick up the phone and the change can be done. So this one material can be used efficiently for structure, for finish, for fire resistance, blast resistance, storm resistance, moisture resistance, acoustics, and more. Masonry may already be on the job, so use it structurally. And in a wonderful way, with environmental concerns going on, masonry is sustainable. It can be made locally, and local materials equal local employment. So this message, why use structural masonry, is the one that we need to get across to all design professionals, including structural engineers like myself. Most engineers know how to design with steel and concrete efficiently, but they don't with masonry. So it's great to be able to educate professionals with current practices in masonry. Let's take a look at some masonry throughout history. This project is the Monadnock Building in Chicago. It was built in 1892. It's 16 stories tall, so 1892, well over 100 years ago. It was the largest load-bearing brick building constructed. It is unreinforced. Now, the walls are 6 feet thick at the bottom, so maybe not so efficient, but it's just to show you that we've been doing load-bearing masonry and tall masonry for a long time. Now, historically, we used empirical design, tables and schedules, and that's something that's been around for a long time. We didn't really start moving into a more engineered design until the 1960s. And even now, some people say you can't do a 2-story masonry building, but you can. Even this old chart shows we could go 8 stories based on empirical design. And as I showed you previously, the Monadnock building was built even taller. And today we can do it even more efficiently and go higher and thinner. Now, the first engineered masonry code was published in the 1960s. Until that time, we were using these empirical standards. We were a little bit behind concrete. So we have been playing catch up a little bit in the perception of engineers for that reason. That's one of the reasons why. And it wasn't until 2009 when Bentley put some of these tools in their software that Force started to model masonry and FEA, and other engineers started going down that path as well. But that was even 10 years ago, and we really should be progressing further than we are today. So let's take a look at just how high you can go with masonry. This is a popular slide. For an 8-inch CMU wall, lightly reinforced, and this example is in a seismic design category A, so of course, if you have higher seismic, then this wouldn't be allowed. But an 8-inch CMU wall, lightly reinforced, can easily be 24 feet tall. And a 12-inch CMU wall, lightly reinforced, can easily be 32 feet tall. If you went with some heavier reinforcing, an 8-inch CMU wall could go up to possibly 36 feet, and a 12-inch CMU wall could go up to possibly 52 feet. And that's what this building is that we're seeing here. This is a high school with a gymnasium wall where the top of wall was almost 52 feet with 12-inch CMU. So if engineers start designing for the actual loads, not pulling from tables, we can create some very interesting and efficient structures in masonry. So masonry is a system, and that system is made up of many components. First of all, there's the block, and block is the basic unit, but it's not the system. So you're going to have strength of block and strength of system that we'll get into later, but it is the main component that gives the wall its strength. Mortar is the glue between the block. It adheres the blocks together. The rebar is there to give the wall tensile strength. Sometimes horizontal joint reinforcement is specified. This is not so much a structural item, but an architectural item in terms of controlling cracking. And then we have the grout, which binds everything together. So this system is very simple to fabricate on site. You can do simple 1-story construction, as you see here. But even in complicated multi-story construction using masonry is simple, even with the openings and the lintels shown in this example. Let's transition into a discussion about the strength of that system. For sustainable masonry design, use off-the-shelf, locally available block strength. And what I mean by that is use what you got. So in this case, F prime M is made up of the individual block strength and then the mortar type. That yields an overall strength of the system. In previous codes, there was a requirement for the block to achieve a minimum 1900 psi of strength. And you combine that with a type S mortar, that yielded a 1500 psi overall strength of your wall. So this 1500 psi has been floating around for a long, long time. Most structural engineers are conservative by nature, and they see, okay, this is the minimum value. That's the value I'm going to use, and I will always meet it no matter what. I'm not going to worry about designing higher. I'm just going to design for this minimum value. But that is an incredibly conservative way to think. Even with older codes, it wasn't that much more difficult to obtain a slightly higher strength of masonry. Individual block values in testing have routinely come up to well over 3000 psi. So the material was already at the strength, but the engineers weren't taking advantage of that strength. And then on top of that, the code was updated, and that 1900 psi is no longer the minimum. It's now going to be 2000 psi. And with that, that yielded an increase in the system strength of an equivalent 2000 psi. So in the current masonry code, the minimum block strength and the minimum design strength are 2000 psi. So that 1500 should be gone. We don't want to see that value used anymore. But some engineers may not know this, and they may still be sticking with that 1500 minimum. Other updates in that version of the code were that for the next tier of strength, the 2500 psi, the minimum block strength was actually reduced from 3750 to 3250. And then for the next 3000 psi level of strength, the minimum block strength was reduced from 4800 to 4500 psi. So it's even easier to achieve these higher overall masonry values. So what we should be doing is looking at what's actually out there. The block data that we see is averaging 3250 or above. So most engineers should be using 2500 as their PSI. So that's a full 1000 PSI over what they have traditionally been assuming. And why is it so important? As I was trying to say, with a higher F prime M, you're going to have a more efficient wall design. Whether or not it's a bearing wall, a non-bearing wall, a shear wall, all of your lintels will be stronger. Your columns and pilasters will be stronger. The lap lengths of the reinforcement in the system will be shorter, and connections to masonry will be much more efficient. So it all adds up. Here's a cost impact analysis that we did showing how a higher F prime M can affect your design. This was a 4-story tall wall with 12 feet from floor to floor. Using F prime M of 1500, 12-inch CMU was required. However, bumping up that F prime M to 2500, which was probably already available and probably already what the strength of the system was, that wall can decrease to either an 8-inch or 10-inch CMU, just depending on which level of the wall we were looking at. That resulted in an 18% savings on an installed masonry cost. So for example, if this was a $2 million masonry contract, that would be $360,000 in savings. Here's another example of an 8-story dorm. In this system, the upper stories were already designed with F prime M of 2000, and they yielded an 8-inch block. But when they got to the lower stories, they required, sorry, let me back up a little bit. When they got to the lower stories, using that F prime M of 2000, it required 12-inch block. And this was not the best implementation of the structure. Those lower areas lost some of their footprint. So what we did is we looked at using F prime M of 3000 psi at the lower stories. And in that case, we were able to keep the 8-inch block walls, which was a big advantage. So in this particular example, they weren't afraid to use higher strength, but you should also not be afraid to specify different strengths as needed in the project. Let's review some of the masonry codes and standards. We already talked briefly about how one of the updates to the masonry code resulted in higher strength available. Another recent update, or at least the 2015 IBC, may or may not be recent depending on where you live. It was adopted, and 2015 IBC adopted the ICC 500, and that mandated that storm shelters for certain geographic areas and certain building uses had to be designed for certain requirements, and this included critical facilities and Group E occupancies, which could be schools. Now, why is that important and pertinent to masonry design? The wind loads that are required by ICC 500, we just took a look at an example here of Texas in the second highest wind speed range are 200 miles per hour. In the Tornado Alley there in the center of the country, they're 250 miles per hour. And if you're trying to design a structure to withstand those wind forces, light framing is not going to cut it. Wood or cold form steel, not going to cut it. Concrete is a possibility, but of course that's going to be expensive. And masonry is a really good solution to resist these forces. IMI actually worked really hard with some testing to look at how masonry could resist some of these wind forces. This was the wall that was used. It was a CMU wall backup and then some brick veneer. And what happened is that you fire a 2x4 traveling at 100 miles per hour through this cannon and strike the wall. In this first image here, you can see that the brick veneer shattered pretty easily, but the backup masonry wall behind it is still intact. And then we'll take a look at a video of what that looks like as well. So the first one will be at full speed, and you'll see that 2x4 being launched at 100 miles per hour into the wall. It's just shattering the brick, but the wall behind it is strong. And then finally at the slowest speed I have here, the quarter speed. So yet another example of where masonry is an excellent material to be used with some of the recent code updates. So moving into some of the masonry systems that are available, masonry is simple but flexible. There are a lot of systems and ways that you can use masonry in today's designs. Masonry load bearing can be a single withe or a cavity wall. Masonry veneer can be anchored or adhered. Hybrid masonry structures where you do have some steel or concrete frame on the site can be used with masonry infill. And then prefabricated masonry is an area where great strides have been made lately. So it gives us a lot of variety and flexibility to use masonry. In our light frame systems, wood and cold form steel, you could use structural masonry in your stem wall, basement wall, shear walls or shaft walls, interior bearing walls and exterior bearing walls. And then in some of these other building systems, the heavier building systems, steel or concrete or precast, masonry can be used in all of those places in addition to interior partition walls. Here's a few photos of some of those structures. This is a structurally participating CMU infill. So we've got the steel frame, but then we've also got the CMU. This is a concrete frame with masonry infill. That was a model created of the system. And here are some prefabricated masonry panels. On this project, the contractor determined that prefab CMU bearing wall partitions would be cost effective for this project. So those were formed on site and then placed. Similarly, these are prefabricated shaft walls. This is very exciting. Instead of having to lay this block at elevation, those prefab shafts can be done on the ground and then lifted into place. Similarly, prefab lintels can be done on the ground and lifted into place, and we will be talking about lintels more later. Stair towers and shaft walls. These occur on most every project out there, and in many, many situations, they are designated as masonry, regardless of what the rest of the material of the building structure is. So let's take a look at how we can use those on our project. So here's a quiz. Which wall requires more reinforcement? The wall on the left has light load and the wall on the right has heavier load. Think about stacking a tower of blocks like kids' blocks. If my kid tries to knock over my block tower from the side, it's easy. But if I push down on the tower and my kid tries to knock it over, it's much more difficult. So the point that we want to make is that masonry likes load. So the answer to the quiz of which wall requires more reinforcement is the wall on the left. For any out of plane load on that wall, without that compression, without that load on it, you're going to need more steel. So let's load up the walls that we have. Not only do they like load and they will be able to help your structure, but that will also reduce the amount of reinforcing that's required in that wall. So here are some illustrations of these shaft towers being used in projects. This was a primarily steel project, and it's a great illustration because you can see those really tall, strong masonry towers standing there, and then right next to them you can see these itty-bitty steel moment frames. Now, whether or not the towers were included in the lateral design, they're still going to take some of that lateral load. The structure doesn't know that the engineer said, we're not using you. When wind blows on it, it's going to resist that wind. So go ahead and take advantage of that. It may require a little bit of additional steel here and there, but you can see from this picture just how flimsy those frames look compared to these robust walls. Similarly, in wood frame construction, there was a tower here, probably for the stair core, and that can be utilized for shear in that region of the structure. And here's an example of a concrete building going up. And in this case, it looks like the towers will also be utilized for shear. Interior partitions. This is a big one for efficient masonry design. And this is another area where engineers for years have been relying on old designs and old schedules. I know when I was in consulting, we had a schedule for our partition walls and a schedule for the reinforcement that went in those walls without even really thinking or designing it. And there are many advantages to using masonry partitions. They can be cost effective and they can be durable, but if we are over reinforcing them, they're going to be too expensive, over designed. Many times we have a bond beam, we have vertical reinforcement at 48 inches on center, and none of this was designed for this particular structure. So let's go ahead and take out all of that unnecessary reinforcement. If this is an interior partition, by code, it cannot take load. You have to detail it at the top so that it does not take any load. So if this is a true partition wall, it's not taking load. We don't need to reinforce it to the level that we have historically been doing. And here are some charts to show the example of this. This is in seismic design category A or B with an F'(M) of 2,500 and then a minimum pressure load from the side of 8 PSF. That's the requirement, the minimum load per the code. You can see that up to 14 feet tall, 6-inch, 8-inch, 12-inch, 10-inch, and 16-inch block don't require any vertical reinforcement. It's probably very counterintuitive to how we've always felt about partition walls, but per the code and per the calculations, that's correct. And then you can even see that going up to 16 feet and 18 feet tall in a narrow 6-inch wall, some vertical reinforcement is required, but even then that's only at 8 feet on center, not the 4 feet that is pretty typical on a schedule. Now, when we get up to seismic design category C, then yes, our reinforcement is going to start creeping up. There is minimum reinforcement required in walls in this seismic design category, but in most cases, again, up to 14 feet high, your bar is at 10 feet on center, not the 4 feet that's specified on most partition wall schedules. And then finally, in seismic design category D, this is where we start to see that 48-inch on center spacing that's pretty typical. And I truly believe this goes back to engineers being conservative and saying, well, we know 48 inches is okay for the worst case. Let's just put it on our drawings everywhere. But that kind of thinking really creates this unnecessarily expensive structure. IMI has a nice free tool on their website to design partition walls. So if you're trying to get a feel for what thickness of wall you would need to be unreinforced, this is a great place to go and do some quick studies. This isn't meant to replace a structural engineer, but it can generally help you to determine some preliminary sizes. All right, moving on to masonry and steel interfaces. We're going to talk about how these dissimilar materials in a structure can lead to some construction and performance issues. This is a picture of a steel lintel in a concrete wall. And when we talk about steel and masonry interfaces, this is one of the first things that comes to mind. And then when we have this case, we're going to have to infill and cover those steel lintels with soaps. And these can be weak spots in the wall in terms of the masonry envelope. Here's another picture from a slightly different view of that face shell. They can get really thin, really wobbly, be hard to stabilize. They're difficult to place. It's hard to maintain. And all the while, you're doing this to cover the steel that is maybe not even necessary in the first place. Here's another picture where a steel column was placed in the wall, and you can see it didn't actually fit inside the masonry shell, and it was too big to fill and cover with masonry soap. So what did they do? They bumped it out and created this unattractive bulge on the inside of the wall. So not only was that steel column probably unnecessary from a strength perspective, but now it's also created more work and kind of an unsightly addition to the wall here. When you are able to fit a steel column in a masonry face shell, it could possibly lead to cracking, and that's not good down the road either. Here's a retail building case study that we looked at. There was a steel frame solution designed, and then we came up with a masonry solution and compared the cost of those two. Initially, it had a concrete foundation and required a 5 to 6 lead time for the steel shop drawings and the fabrication and delivery. There were 54 steel columns, and it was a complicated foundation layout. In the masonry solution, we looked at a CMU foundation, and we looked at 8-inch CMU load bearing with a 4-inch veneer, and that reduced the number of steel columns required to 9. It's a huge reduction. And the lead time was less than 4 weeks for all of the masonry. It was 4 weeks, so that would have been faster than just the shop drawing time for the first steel frame solution. That resulted in a $40,000 savings, and the developer liked it so much that it became a new prototype for additional structures. Lintels. This is a big one when we're talking about cost. So what are the typical lintels that you see in a masonry project? And what should you see in a masonry project? Number one, masonry. Makes sense, right? You've got a masonry project. You might have some masonry lintels there. This is the best solution architecturally and structurally in the majority by far of all the lintels that you see in a masonry project. Number two is steel. And this one is actually by far the most common, but it's generally not needed. And it creates complexity. It ends up being perhaps more trouble than it's worth. And then a third option will be precast masonry lintels. So let's look at the steel lintel first, because that's the one that's most common on job sites. This also goes back to a scheduling thing. I'm sure there are many sets of structural drawings out there that have a steel lintel schedule. It says openings up to 3 feet, use a W8 by 10. Openings up to 6 feet, use a W10 by 12, et cetera, without ever performing any sort of analysis to see what the actual size is that's needed. So it's super common, but it really shouldn't be. As we mentioned, steel has a longer lead time than masonry. You have to conceal it with masonry soaps. It becomes a weak spot where it connects back to the masonry. Steel will end up moving differently than masonry. Sometimes you can have thermal bridging issues across the cavity there. So why are we using it so much? These are all the items that I just mentioned. And for example, this is a bearing plate of a steel lintel on a masonry wall. If that bearing plate had been designed for a concrete wall, it could have been only 1 inch thick, but the masonry design ends up being 2.5 inches thick. It became huge. But if you use a masonry lintel, then the bearing plate actually goes away. Here is another typical detail for a steel lintel, and it's critical that the size of the steel lintel be considered. The depth needs to match the coursing. The width needs to consider the needed blocks to conceal. There's a lot going on here. Sometimes if you have this shelf angle, that can lead to torsion in your steel lintel, and oftentimes that is overlooked. You could use a tube, but then it's even harder to conceal that steel tube within the face of the masonry wall. And yet another detail that shows all the, quote, moving parts of getting a steel lintel attached into a masonry wall. You might get a detail that looks like this. A bearing plate that allows differential expansion. The steel will expand at a different rate than the masonry, but it probably won't slide long term because the steel is going to get wet and rust. And when this steel beam tries to contract, it's probably going to create a crack where your anchor bolts are tied into your masonry. And then your jam height in your masonry should go full height, but we're not able to do that with the bearing plate and the lintel resting right there on the edge of the wall. And of course, those bearing plates are often way too big. Torsion, as we mentioned, is an issue. Sometimes if you have a W shape in there, torsion can create real issues. And yet here's another example of trying to fit that steel lintel into your masonry wall. There's that crack that we talked about where the bearing plate bolts are embedded in the masonry. In this case, coursing, they didn't want to have to cut the block, at least I'm assuming that's what happened here. So they just shifted the whole lintel over, which defeats the purpose of the lintel in the first place. Here you see a perfectly strong masonry wall with pilasters in between the windows and not even that long of a span, and yet they decided they needed a steel beam, which then required the addition of those steel columns, which then had to be carried all the way to the ground. Here's another example of the crack occurring where your steel lintel ends and the bearing plate is installed. And to prevent that crack, you should use masonry. Or if you absolutely can't avoid it, then you need to move your control joints away from the corner of the wall. And we will talk more about that later. It's complicated. That's what you should take away from the steel lintel. There's an image of the steel, the anchor bolt, the U-bars that have to hook back to the jam bars, which had to be moved away from the edge of the wall. Why not just use masonry? It's strong enough. In door openings of 3 feet, it's easily going to work. Even spans of 6 to 10 feet are easily going to work. It's fast, it's economical, it matches the wall. It moves with the wall, unlike steel. It can be built in place or it can be prefabricated. Like I said, 6 to 10 feet is easily possible. Longer spans are possible. There was even a 12-foot common in a recent Detroit school prototype. And then there was one that was even 52 feet long in Wisconsin. Of course, that one was 12 courses high, but it just goes to show that it can be done. And this would be the much simplified detail for a masonry lintel. So many fewer moving parts. It's inherently more robust, and it's a lot stronger. One of the other considerations for a steel lintel is that you don't have any arching action to take the load over the wall. The full load is bearing on the lintel. You can see the control joint there at the right-hand side. That's required when you have a steel lintel. And in that case, the full weight over the lintel bears on that lintel, and it has to resist all of that weight. However, if you have a masonry lintel, you no longer need that control joint, and actually you should move it away from the edge of the wall, which we'll talk about more later. But now you get this fixed end and you get an arching action. So you're actually resisting less of the force on the lintel itself, and some of that force is being distributed to the sides of the opening. Here's another picture of a crack, and if that control joint is moved away from the opening, that crack won't happen. There's a misconception with one reason that contractors use steel lintels is that they won't have to shore it. So they can put the steel up and then they won't have to shore the masonry. But there are workarounds to that problem. This is just one picture that is shown here where they have some steel angles turned upside down and they're building the masonry lintel on top. And then once it's set, they can slide those angles out. You can see the paper there so that they will be able to slide them out and then just infill and remortar those joints. Precast lintels are another option, and you can either build those on site or bring them in from a manufacturer. It's definitely a coordination effort, but at least then you don't have the dissimilar material of steel and masonry happening. You will probably need a crane or lift access, but it has a nice compatible aesthetic with the masonry. You do have to consider modularity with the masonry, and if it is a precast prefab lintel, special anchoring may be required to prevent roll-off. Here's one of the products that works really well that you could install. We're not going to get too much into details on these, just wanted to show you some of the options available. Here is a prefab lintel that is being lifted into place. That's where you're going to need that crane. Here's one being constructed at ground level and then after being lifted into place. So let's talk a little bit about those movement joints. I've said a few times now that you want those control joints to be moved away from the edges of the masonry. In the masonry code, it does say that structural engineers are responsible to locate control joints for the structural masonry. So the architect is not responsible for that. The architects are generally responsible for locating the expansion joints or movement joints for veneer, the non-structural masonry. And if you have notes that locate your joints, such as 10 feet away from edges and such a distance away from corners, it's generally not enough information for the contractor. We highly recommend that you show those joints on your drawings. For veneer, again, the architecturally specified joints, they can be made up of vertical joints and horizontal joints. And the vertical joints are needed to prevent cracking when there's differential support, and you would rarely eliminate these. The horizontal joints are needed if you need to allow for differential movement. It's not meant to relieve bearing on the masonry below, and in some cases it also can be eliminated. Here's an example of a vertical joint in veneer. The wall on the left is supported by the foundation. The portion of the wall on the right is supported by a shelf angle, so you need that expansion joint there when there's that differential support. Here's a real-life example of that. We're calling it an isolation joint, expansion joint. Part of this wall is bearing on the foundation, and part of the wall is bearing on a steel angle or some kind of ledger bolted to the wood. So that differential movement needs to be isolated. There should have been some kind of isolation or control joint, expansion joint, whatever you want to call it, along a plane like this. Now for the structural masonry part of joints, we again have vertical joints. So in veneer, they're needed for cracking, differential support. In structural masonry, they're also needed to prevent cracking. They can also be used to isolate a structural element. And in some cases, we can either eliminate them or move them to where they make more sense. For horizontal joints, in veneer, there were some instances where they were necessary, but in structural masonry, a horizontal joint is never necessary. Usually you see complicated details like this. A horizontal joint, thinking that they have to relieve some of the masonry weight above from bearing on the masonry wall below, and you've got some crazy steel angle back into the structure. It's not necessary, and you look at it in construction, it just doesn't even seem to make any sense. So again, never Horizontal joints are never required for structural masonry. And vertical joints in structural masonry serve to isolate a structural element. We want to move those away from the edges of the wall. What you're seeing right now is sort of an old school example where you put a vertical control joint at the edge of every opening. And basically what that did in this situation is it ended up turning this nice long wall into a series of very narrow, tall panels. And these narrow and tall panels are not able to resist much lateral movement. They're too isolated from everything around them with all of those control joints in place. What we want to see, especially now that we have finite element software where we can take advantage of quick calculating, is to put control joints away from the openings and just put them at a regular spacing so that we now have a series of more, where the height to width ratio is more uniform for these, or closer to 1 is what I'm trying to say, for these walls. And we call this a perforated shear wall. Yes, there are still going to be openings in it, but overall the wall is going to deflect much less. This is a little animation of a software example. So you can see that with the lateral deflection of the lower portion, which are the tall, skinny piers, they deflect much more than the overall wall at the top. Even though it has the same skinny piers on the bottom, if that can be considered one element, the deflection is much better. And then finally, for control joints in masonry cavity walls, the expansion joint on the veneer and the control joint on the masonry don't have to align. So you don't have to worry about that. There's that cavity there. The ties that tie any veneer back to the CMU are flexible enough to allow for any horizontal or vertical movement between the two. So there's a lot of movement factors to consider, but if the structural engineer worries about their part and the architect worries about their part, then even in a cavity wall, you don't need to align those joints. All buildings are going to move. The concrete masonry may shrink and the clay bricks may expand, but as long as those joints are in place, they don't have to align. And with that, we have come to the end of the presentation. Some conclusions to take away: use your available F'(M). Use what's there or use higher if you need it to get into the 2020s. The strengths are there. We should be relying on them and should be utilizing what's available. Design by current methods. Use software, not tables. Don't rely on those old, outdated schedules. Take the time to do a quick calc, and you will find that your savings will be significant. If you have masonry on a project, use it. If you have a shaft tower or something that's there, use it. Bear on it, use it for lateral. It likes load and it will benefit your structure. Don't over reinforce your partition walls. Take a look at any existing schedules that are on your drawings and update those so that this unnecessary reinforcement is not in the majority of your projects. And then finally, consider masonry strength for lintels and columns. Again, if the masonry is there on the project and it can take the load, let it. It will be a stronger project and it will be less costly in the long term. I appreciate your time listening today. I really enjoy working with engineers and architects and hopefully making a difference. And the goal here is to make other design professionals even a little bit better, a little bit more efficient. And I hope I did that for you today. Thank you.